Okay, so what we will do now is continue with the importance, continue discussing the importance of local rings. So, again, just to recall, you start with a variety capital X and a point small x, then you have the local ring of capital X at small x, which contains the ring of regular functions, global regular functions, namely regular functions that are defined on all of capital X, and which in turn is contained in the function field of X, okay, which turns out to be the quotient field of the local ring as well. And now the local ring, so the point is that the local rings contain a lot of information, that is the idea. So what we saw in the last lecture is how local rings capture isomorphisms. Of course, an isomorphism induces isomorphisms at the level of local rings, and conversely if a morphism induces isomorphisms at the level of local rings and it is a homeomorphism, then it is an isomorphism. Okay, that is what we saw. Now what I am going to show is I am going to discuss local rings and regular functions. I am going to say that if you take an element here, namely an element which is a rational function, that means it is a function which is regular on an open set, and suppose this element is here for every local ring, then it is actually defined on all of X, so it is a regular function on all of X. So it is very clear that if you take a regular function on all of X, then a regular function is of course a rational function, because after all by definition a rational function is just a regular function defined on an open set, and since if I take a global regular function that is defined on all of X which is also an open set, so any regular function is always a rational function, and any regular function is going to live in every local ring, namely that regular function is going to give you its germ in each local ring. So something here is going to be in each local ring, and of course it is going to be here as well, but something here, when is it here? The condition is that this, if that lives in every local ring, then it is here. Okay, so let me state that. So that is another important thing. So to check that a function is defined everywhere, if you can somehow check that it belongs to every local ring, then it is defined everywhere. Okay, and the reason why you are able to do that is because all the local rings sit inside the quotient field. All the local rings sit inside the quotient field. So let me write that here. Local rings and regular functions. So here is a theorem. So the theorem is let X be a variety an element of kx that is in the subring Oxx for all small x in capital X is actually in Ox. So, so this is a theorem. It says that you take an element here, namely a rational function. If it is in every local ring, then it has to be a global regular function. Okay, so for the proof, so what I want to tell you is that see, if you think of it philosophically, it's quite you can even think that this is obvious or even tautological. Okay, philosophically what you are saying is that you have a rational function, namely a function which is defined on an open set, but you are saying that it is equal to the germ of a regular function at every point, which means you are saying that it lives in a neighbourhood of every point, and that is the same as saying that its domain of definition, that is a maximal open set where it is defined, is all of x, which means it is actually the open set where it is defined is not just a proper open subset of x, but it is actually all of x, which means it is a global regular function. Okay, so that is the philosophy, but then it involves a little bit of commutative algebra, and that is what I want to tell you. See, the important thing is that, you know, trying to say that a rational function is defined at as a regular function in a neighbourhood of a point is the statement that, you know, that this actually belongs to this subring. Okay, the fact that an element here belongs to a subring like this is another way, is actually the commutative algebraic way of saying that the rational function is actually defined in a neighbourhood of the point small x. Okay, that is, or it can be extended to a neighbourhood of the point small x. Okay, so so, you know, trying to say that a rational function is defined at every point is, if you want to say it commutative algebraically, how do you say it? You say it like this. You say that the element of the rational function defines an element of kx, and you are just requiring that it is in each of these subrings. I mean, if it is in one such subring, then that is equivalent to saying that it is defined in a neighbourhood of the point small x. Okay, so the problem with a rational function is that it could be meromorphic. Okay, namely it could have it could be a quotient of regular functions, and it may not be defined where the denominator function is vanishing. Okay, and therefore it need not extend to all of x, but the fact that it extends to a point is reflected by saying that it belongs to this subring. Okay, and that is the content of the theorem. So so let me do the following thing. So what I would first like to say is, so we will use this fact, namely any variety is covered by affine varieties. Okay, any variety is covered by open subsets, and in fact finitely many of them, each of which is isomorphic to an affine variety. So what I will do is I will go from x to, you know, I'll first take the case when x is an affine variety. Okay, I'll first solve the theorem for the case when x is an affine variety, and then I will say that therefore it also solves the case when x is a general variety, because a general variety is a finite union of affine varieties. Okay, so first assume x is an affine variety, say x equal to max spec a of x, a of x is equal to a, say. So you know, this is how you recover an affine variety from its coordinate ring. If x is an affine variety, you have Ax, it's affine coordinate ring, and if you take the maximal spectrum then you get back the affine variety. Okay, so in fact, so if you want, X is sitting inside some affine space as an irreducible closed subset, and Ax is the coordinate ring of X. Okay, it's the regular functions on the affine space, namely polynomial ring in as many variables as the dimension of the affine space modulo the ideal of the closed subset, irreducible closed subset, which is a prime ideal. Okay, so A is an integral domain which is a finitely generated K algebra, right? And now what happens is that you have so you have a situation like this. You have Ax which is equal to Ox, that is A for us. Okay, because if X is affine, Ax is the same as Ox, and that is A, and that is sitting inside Oxx local ring. Okay, and mind you, this local ring, well, I'll rather write it here. Okay, and this is sitting inside Kx, this is the function field, right? And how does all this translate? Well, Ox is Ax, which is A, and then the local ring is Am, okay, where M is the maximal ideal of A that corresponds to small x. So after all, small x is an element in capital X which can be thought of as a maximal ideal in Ax, okay, which is A. So this is just Am. Okay, this is the expression for the local ring at a point on an affine variety where the point corresponds to this maximal ideal M. Okay, and what about the quotient field? This will be I will get Q of A. You have the quotient field of A, and that will be the same as the quotient field of X, the function field of X. Okay, so this, and mind you, QA is the same as QAM. If you have an integral domain, then the integral domain, every localization of the integral domain is also an integral domain, and the integral domain sits inside as a subring in its localizations, and all the localizations have and the integral domain itself, they all have one and the same quotient field. Okay, so this is A is an integral domain, Am is localization at the maximal ideal M, which means that you invert everything outside the maximal ideal, and both A and Am have the same quotient field, okay, Q of A. Okay, and that identifies with the function field of X. Okay, and now what's happening is that I have a so what is given to me is a rational function which so this is a little bit of simple commutative algebra, but the point I want to make is that that whatever commutative algebra, little simple commutative algebra that we are doing is beautiful enough to give us this result. Alright, so you start with the rational function here. I mean, you start with the rational function here. By definition it's here, so it is of the form f by g. Okay, so I start with an f by g here. Okay, I start with an f by g here because because this rational function is an element here and this is identified with this, I am easily able to write it as f by g because it is the quotient field of A, where f and g belong to A. And what is given to me is that this f by g belongs to Am for every maximal ideal M. That is what is given to me. Okay, so f by g is equal to, well, an element here. Okay, and an element here, well, let me write this as f sub m by g sub m in Am for every M maximal ideal. So max spec is the set of all maximal ideals of A, and for every maximal ideal I have this local ring, and this f by g belongs to the local ring means the f by g is equal to an element in the local ring. Alright, and an element in the local ring is written like this, where the denominator is not in the maximal ideal. Okay, this is given to me. What I will have to, what I will have to do, I will have to show that this f by g is actually in A. Okay, I have to show that this rational function I started with is actually here. Okay, so I have to show that f by g belongs to A, which means I will have to show that I have to actually show that I have to show that g divides f. Okay, if I show that g divides f, okay, then that's the same as saying f by g is an element of A, and that will show that f by g belongs to A. So I will have to show that g divides f. Alright, so we need to show f by g belongs to A, that is that, well, g divides f in A, or in other words you just have to show that f belongs to the ideal generated by g. This is what you will have to show. If f is a multiple of g, so f by g is an element of A. Okay, that is what you will have to show. Now you see, now let's analyze this. Of course, if g is a unit, there is nothing to prove. If g is a unit, there is nothing to prove, because then f by g is f by a unit, okay, and f by a unit is also an element of A. Okay, so assume that g is not a unit. So assume g is not a unit. Since g is not a unit, it means that every non-unit is contained in a maximal ideal. Okay, so there exist maximal ideals M which contain G. Okay, there exist maximal ideals M which contain G, and so for such maximal ideals M, you look at this equation. So what you will get is, you will get f gm is equal to g fm for such M implies, what does this imply? So you see, G is in the maximal ideal M, okay, and therefore this right hand side is in the maximal ideal M, therefore the left hand side is in the maximal ideal M, but a maximal ideal is prime, and therefore one of them has to be in M, but Gm is not in M, therefore F has to be in M. Okay, so this will tell you that, well, F will have to be in M for every M maximal which contains G. You have this, okay, and anyway, but what is very, very important is this condition. Even if I take an M which may or may not contain G, okay, perhaps this is just an observation that comes from this equation, but what is more important is this condition, that for every maximal ideal I am getting an element outside that maximal ideal, and the beautiful thing about that is that whenever you give me one element out of each maximal ideal, then this collection of elements actually generates the unit ideal. Okay, that is a crucial topological fact. It is the same as saying that all the basic open sets defined by all these GMs, they cover the whole space. Okay, see, now, so let us not worry about this observation for the moment. Okay, let us look at this. See, you take Gm does not for every M in max spec A, which is actually X, there exists Gm which is not in M. that is what you have here, alright. And now the claim is the set of all, you take all these GMs where M belongs to M is a maximal ideal of A, the ideal generated by this is actually A itself, it is a unit ideal, okay. And the answer is, I mean, why this is true is very simple, because you see, if you take the ideal generated by all these GMs, the ideal generated by GMs, if it is not A, if it is not the unit ideal, then it is a proper ideal, right. An ideal which is not the unit ideal is a proper ideal, and you know any proper ideal is always contained in a maximal ideal, therefore this ideal will then be contained in an M naught, okay. But then Gm naught will be in this ideal which is contained in M naught, but by definition Gm naught is not supposed to contain not supposed to contain be contained in M naught, and that is a contradiction, okay. So let me repeat it, if this is not A, then this is contained in an M naught where M naught is a maximal ideal, okay. And then the problem is that Gm naught is in this collection and that will be contained in this which is contained in M naught, but Gm naught is not supposed to be contained in M naught, you get a contradiction. Therefore this ideal generated by all these GMs is A, okay. This is just equivalent to, so let me also say that this is equivalent to X is given by the union of all the D GMs where M belong to max spec A, because what you should understand is, you see if GM is not in M, okay, you look at DGM. What is DGM? DGM is the basic affine open set where the function GM does not vanish, okay. So it is the same as saying that the point corresponding to M is in the basic open set defined by GM, okay. So but I have covered all the points, I have taken all the maximal ideals, so I have covered all the points, and for each point I have this DGM. So you know, if you draw a picture, this condition is actually like this, I mean it is a bad picture which is very only said theoretically descriptive, but it is not a correct picture, but it is correct enough to think a little. So you have to give you some basic idea of how things are. So you have X given any point M, okay, you are thinking of a maximal ideal in A as a point of X, okay, and for this every point you are able to find this DGM which is an open subset which contains that point, alright. That is what it means to say that GM is not in M, that is what it geometrically means. And since you have covered every such point, the union of all these DGMs will be X, okay. But then you know Zariski topology is quasi compact, therefore only finitely many GMs have to cover X, but the fact that finitely many GMs cover X is the same as saying that those finitely many GMs will generate the unit ideal, okay. So which is if and only if X is equal to union of I is equal to 1 to L D GMI. So here I will have those G, it is the ideal generated by DGM1 etc. up to D I mean up to GM sub L. So if something is a unit ideal, then one can be generated by finitely many GMs, call those GMs as GM1 through GML, then the ideal generated by GM1 through GML contains 1, so it is the full ideal A. But then writing A is equal to the ideal generated by GM1 through GML is topologically equivalent to writing max spec of A, which is X, is union of all the affine opens defined by these GMIs. That is what is the topology that is involved, okay. So you can see side by side algebra and topology going hand in hand for the Zariski topology. Now if you look at it carefully, what you get is, well, therefore what you get is therefore there exists f mi, so let me use something h mi in A such that sigma h mi g mi is equal to 1, I equal to 1 to L. This is what it means to say that the GMIs generate 1, okay. That means a ring linear combination of the GMIs is equal to 1 for a suitable ring linear combination, okay. Now you know, but then you see now I can use this, I can take f by g is equal to f by g times 1, where you know I am doing all this computation here in the quotient field, okay. Whatever equations I am writing now are valid in the quotient field. So f by g is f by g times 1, and the 1 in the A is the same as the 1 in the AM, is the same as the 1 in the quotient field, okay. So this makes sense also in the quotient field, so it is f by g sigma I is equal to 1 to L h mi g mi, because after all this is 1. Now I push it inside, I will get sigma I is equal to 1 to L f by g times h mi g sub mi but you see I have f g mi is g f mi, alright. So so this is going to be sigma, so you know if I can write the sigma I equal to 1 to L f g mi h mi by g, but that is equal to sigma I equal to 1 to L f g mi is actually g f mi by g, and well g cancels out, and what you get is I get sigma I equal to 1 to L f mi h mi, which is actually in A, this is an element of A, okay. So what I have done is I started with f by g in kx and I proved it is actually in Ax, so it's actually a regular function, okay. So so this settles the case when x is affine, okay. Now when x is not affine, you know that x can be covered by finitely many open sets, each of which is affine, and what this argument will tell you is that on each of those affines the rational function will be a regular function, okay. And what it will tell you is that the regular function lives on all open sets of a cover, okay, and it coincides, and it will of course coincide on the intersections, therefore it will give a global regular function, okay. So so that finishes the proof in the general case, okay. So let me write that down. This settles the case when x is affine, okay, when x is general, x is a finite union of open subsets, open affine subsets, okay. If x is a general variety, then we have seen that any general variety is a finite union of open affine subsets, and by what we just proved, the rational function, okay, the rational functions will not change whether you consider rational functions of x or rational functions of any open subsets, okay. Therefore what you will get is that the rational function you started with actually is a regular function on each affine open set, which all of which form a cover for x, and of course on the intersections also it will give the same function, because everything is finally happening in the quotient field which is the same, okay. So basically what will happen is that you will get a regular function on each affine open subset by the previous argument, and all these regular functions will coincide on the intersection, then therefore they will define a global regular function. After all, a global regular function is a global function which is locally regular, okay. So to define a regular function you have to just define it on an open cover, okay. So so the case when x is general is also covered, okay, and so that is the general case, okay. You know, if you want maybe I can even write something in symbols so that you are a little bit more convinced comfortably. So you know x is union I say j equal to 1 to m xi, where each xi inside x is open affine, which means that each xi is an affine variety, each xi is an open subset of x which is isomorphic to an affine variety, and then you must understand that you know kx is the same as kxi for every I, okay, and O capital X small x is the same as O capital X small xi, O capital small x capital Xi comma small x if small x is in xi. The you know the local rings and the function fields don't change if you go to open sets, okay. So what will happen is that if you start with an element of kx, it will belong to, and it can be thought of as an element of kxi for each I, but because each xi is affine and it is in each local ring, by the previous argument it will be in oxi for every I. So you will have an element of kx which is in oxi for every I, but then that will mean that it is actually in ox, okay. So and a phi in kx is equal to kxi belongs to oxi for every I by the affine case above, and thus to ox, and that's the end of the proof, okay. So after all you know, to define a function you have to only define it on an you have to define functions on open sets which agree on the intersections, okay. And similarly to define a regular function you have to give me a regular function on an open cover which agree on the intersections, and that is what happens here, okay. So this is a very nice fact, that to conclude that a rational function is actually a global regular function, that it is defined everywhere, you just have to check that it belongs to every local ring, okay. So that is another, that demonstrates another important power of the local ring, okay. Then the next thing I wanted to tell you about is something that is far more profound. It is the following thing. See, the you can see that somehow the very word local ring will tempt you to think that it somehow encodes all the local information at the point, but the problem is local information, if you want to think of it as a information on an open set containing the point, you must remember the open sets are huge for the Zariski topology, because the open sets are, after all, every open set is irreducible and dense, okay. Therefore if you take an open neighbourhood of a point, it is not a small neighbourhood, it is not small in the sense of usual topology, it is not like having a smaller and smaller disk or smaller and smaller interval of a point on the real line, or having a smaller and smaller disk of epsilon radius of a point on the plane, it is not like that. Every open set is huge, therefore the fact that the local ring stores such information should tell you that it is actually having much more than local information. So the truth is that the answer to that is yes, it actually also stores information on a huge subset containing the point. So that is the power of the local ring. So what I am going to next state is this very beautiful result. It says that take two varieties x and y, okay, and take a point of one variety, take a point of the other variety, take a local ring at this point for this variety and take a local ring at that point for the other variety. If just these local rings are isomorphic, okay, then there is a whole open subset containing this point in this variety and an open subset containing that point in the other variety which are isomorphic. So if two local rings are isomorphic, if the local ring of a variety at one point, just the local ring alone is isomorphic as a K algebra to the local ring of another variety at some other point, then a huge open neighbourhood of this point on this variety has to be completely isomorphic to a huge open neighbourhood of the other point. So even isomorphism of local rings is actually in this sense pretty global, okay. It tells you that if two varieties have 2 points which are whose local rings are isomorphic, it means that these two varieties are on an open set, on open sets they are actually isomorphic. That means the only place where they are not isomorphic is a boundary, okay. So that is another powerful property of the local ring. So let me state that. So local rings, so I will call this local rings and birationality. So local rings and birationality, okay. So let me define this notion of birationality. Birationality, two varieties are called birational if there is a non-empty open subset of each which are isomorphic, okay. So x varieties x and y are called birational if there exists u open in x, of course non-empty, and v open in y, of course again non-empty, such that we have an isomorphism of varieties u to v. Okay. So two varieties are birational if there is an open subset of one which is isomorphic to an open subset of the other. See, the varieties themselves need not be isomorphic, but the point is there is a huge open set of this of each of these which look the same, okay. That is the concept of birationality. Now what you must understand is that this notion of birationality is it's actually an equivalence, because you know if x and y are birational, that is of course symmetric, okay. X is birational to y is the same as y is birational to x, and of course an isomorphism is always if two varieties are isomorphic they are of course birational, because you can choose the open sets to be the whole varieties themselves. So the notion of birationality actually it is a relation which is an equivalence relation. If x is birational to y, then y is birational to x. Any variety x is always birational to itself by the identity map, which is an isomorphism, okay, and if x is birational to y and y is birational to z, then x is birational to z, okay, because any two open sets will always intersect, okay. So if you have an isomorphism, if u inside x is isomorphic to v inside y and v prime inside y is isomorphic to w inside z, then you can get the isomorphism composed on v intersection v prime, which will be non-empty, okay. Therefore this birationality of varieties is an equivalence relation, okay, and if you take the set of all varieties, if you take the category of all varieties and then you go modulo this equivalence, you get what is called the set of birational equivalence classes of varieties, and actually it is the first step in classification of varieties is to find in each birational equivalence class a variety with say good properties, for example a variety which is smooth, okay, and so you know, basically whenever we study objects in mathematics we always ask the question how many non-isomorphic objects are there, okay. So or in other words you try to describe the set of isomorphism classes of objects, okay. This is called the classification problem. So you can ask the classification question for varieties. You can ask, you take all varieties and you go modulo isomorphism, then you get the set of isomorphism classes of varieties. What is that set, okay. Now the fact is that that's not a very easy question, okay, and in fact the first answer is to, instead of going modulo isomorphism which is very strong, you try to first go modulo a weaker equivalence relation like birationality. So you first ask the question what is the set of birational equivalence classes of varieties, okay. That brings down the problem to a more tackleable level, okay. So birationality is very important in the classification of varieties. So let me write this down. Birationality, it's easy for you to check that is an equivalence relation, okay. And now comes the theorem that I wanted to state. The theorem is let x belong to x, small x be a point in capital X, small y be a point in capital Y, such that of course x and y are varieties. OXX, the local ring of capital X at small x, is isomorphic to OYY, isomorphism as K algebras. So I just have two varieties capital X and capital Y and points small x belonging to capital X, small y belonging to capital Y, such that the local ring of capital X at small x is isomorphic to the local ring of capital Y at small y by an isomorphism which is a K algebra isomorphism, okay. Then the result is that there is an open set U in X, in capital X, which contains the point small x. There is an open set capital V of Y which contains the point small y, and there is an isomorphism of varieties from U to V which under pullback of regular functions at the local rings induces phi, okay. So then there exists U in X open, V in Y open with X belonging to U, Y belonging to V, and an isomorphism of varieties so let me use so let me use a different symbol for this. So let me call this something, let me call this a psi. phi from u to v such that phi hash y is actually psi. Well, psi inverse. Okay. So it's a very powerful theorem. What it says is that if one local ring of one variety is isomorphic to another local ring of another variety, then these two varieties are birational. They are the same on huge open sets, they are the same, okay, and that tells you how much information a local ring contains. Just isomorphism, we think of local ring as something that's concentrating attention at a point, but this tells you it's much more than that. Just local ring at one point of one variety being isomorphic to local ring at another point of another variety is enough to say that these two varieties are the same on a huge open set, except for a boundary they are isomorphic. Okay, so that's the fact that gives you that the fact that local ring contains a lot of information, even more or less global information, as in the sense that it contains information on a big open set. Okay, so one needs to prove this, and again the beautiful fact is that this also involves a lot of commutative algebra, but pretty easy commutative algebra involving localizations, and it's very the proof is not very difficult, but the point is that you can just use nice commutative algebra to capture these two open sets as nice basic open sets, okay, which are isomorphic. Basic open sets containing those 2 points which are isomorphic. Okay, so let's do that in the next lecture.